Rust is a systems programming language being developed at Mozilla. Rust has features of a high-level functional language like Scala and a low-level performance-driven language like C or C++. My guest, Steve Klabnik, is a developer program member with Mozilla. In this episode, he discusses how Rust looks at memory management, type safety, mutability, and concurrency. We also dive into a discussion of the low-level virtual machine, also known as the LLVM, which the language Swift is also built on. You can write compilers for programming languages using the LLVM. If you're a fan of Software Engineering Daily, please share the show with your friends, tell them about it through Twitter or Facebook or email. You can also rate the show on iTunes. All of these things help our show grow, and that translates to revenues for the show through advertising. And those revenues get put back into the show, that I reinvest them, much of them, the portion that is not used to live, because the show will continue to grow and I'll expand into more forms of content. So let's get on with this episode. Rust with Steve Klabnik. I had a crazy idea a couple weeks ago. It's a photo sharing app that only has pictures of cats. When I finish my photo sharing cat application, I will be deploying it to Linode, because Linode is the fastest hosted Linux provider. I don't want to get locked into a proprietary platform that's going to overcharge me as soon as my app gets popular. I just want a fast Linux server with simple pricing. Go to linode.com/sedaily and get $20 in free credit today. Plans start at $10 a month, so my free $20 will be plenty to launch my cat photo sharing app. Once I need to scale, I can use tools like node balancers and backups, and Linode has built-in dashboarding and metrics so that I can see the traffic to my Linode servers, and I can understand how many of my users are posting cat pictures and looking at each other's cat pictures. Go to linode.com/sedaily and get $20 in free credit today. The plans start at $10 a month, so it's a great deal. Thanks to Linode for sponsoring Software Engineering Daily. Now let's get on to this episode. Steve Klabnik is a developer program member with Mozilla. Steve, welcome to Software Engineering Daily.
Yeah, thanks so much for having me on.
Rust is a systems programming language that is being developed at Mozilla, where you work, and Rust is the topic of our conversation today. What are the goals of the Rust programming language?
So you can sort of approach this from two directions. I'll go from the pitch first. So you already mentioned systems programming language. That's sort of a little complicated, so we'll just put that on the table for now. But basically, Rust's main three focus points as a language are on safety, speed, and concurrency. And so we usually talk about those three key points as like why the language exists. The systems thing falls out of these kind of requirements, but it also means different things to different people. So it's also, I've been wondering if we shouldn't stop describing Rust as a systems language, because sometimes it seems to introduce more confusion than it helps with. So I don't know if you want to talk about that or like talk about Mozilla's usage of Rust, or how we should, which way you want to go into that. Because it's a big conversation. Like this is the point.
Absolutely. Well, it's not just a systems language. It's not just a low-level language. It's also a high-level language. So it's unique in that sense. You've described it as a mix between functional programming and C, and we think of functional programming typically as a feature of high-level languages. What are the desirable aspects of functional programming, and what are the desirable aspects of a low-level systems language like C, and how are both of these things captured in Rust?
Yeah, so it's interesting, and this is also a hard part of describing it, because traditionally, when you talk about low-level languages, programmers are we have developed this understanding that low-level languages need to be painful to actually use, and that's just an inherent part of the problem domain, and there's sort of no getting around that. So one of the hard parts about this discussion is accurately representing Rust's low-level cred, while also sort of emphasizing that in the day-to-day, it's actually not nearly as difficult or maybe as complicated or as hard to use as traditional systems languages. So the first thing, and the thing that I guess is most important, as I mentioned, low-level cred. So it's very important to us that Rust is good for doing development at all levels of the stack, but sort of trending toward the lower level ones. So for example, I have a hobbyist operating system project that I'm working on in Rust, and it works well for that use case. And so that's sort of kind of what we mean by systems is you can truly build any part of the software stack and there's no complicated runtime requirements or heavyweight stuff added on top of that and all these things. In terms of the functional programming stuff, it turns out that when one of the problems in low-level programming is that there's a lot of things like global mutable state or details that you need to get absolutely perfectly correct. And traditionally speaking, systems programming languages have not had the best type systems. C's type system is there, but it is not particularly strong. And so one of the areas that functional programming gets really right is that it enables you to deal with problems at the type system and therefore at compile time instead of runtime. And functional languages has historically had a garbage collector and a relatively heavyweight runtime. But one of the interesting things about type systems and compile time checking is they pay no runtime cost because you do all the checking up front. So one way of thinking about Rust is using the tools that functional programs give us in order to produce extremely fast code by sort of relying on this low-level nature. And that's really what enables Rust to be both safe and fast at the same time, is that a lot of the safety checks are done during the compile step rather than at runtime.
We can characterize the language further by talking about the users of Rust. And there are three different camps of people that tend to check out Rust. And those are C++ users, and then Haskell users, and then people who just like building web applications, whether that's in JavaScript or Ruby. So these are three very deep verticals, and they're very unique verticals. So it's interesting that they all pursue Rust, despite being highly verticalized. C++, Haskell, and then JavaScript, Ruby, web app types. What are each of these three distinct user types? What are they looking for when they seek out Rust?
Yeah, so this thing is something I always find really interesting, and one of the things I like to emphasize about it is each of these three groups both is looking for something in Rust, but they also bring something to the table that they kind of give to Rust as well. And so, yeah, I sort of see these three main sort of groups of people as user profiles of constituencies for sure. So I'll start with the systems people. So the C and C++ programmers, they come to Rust because in some ways, and maybe this is a little too strong of a statement, but I like to think that Rust is sort of one of the first true contenders to C++ in its space. And what I mean by that is we've had a lot of languages that have wanted to sort of chip away at C++'s mindshare. And in fact, a lot of languages have as well. I'll get to that in a second, I guess. But almost all of them have included a garbage collector, which for the way that hardcore C++ people write C++ is basically a non-starter. And so they haven't seen a whole lot of movement away from that space. What I will say is that over time, all languages have kind of chipped away at C++'s mind share. In the late 90s, if you were writing a program, it probably was in C or C++. And then with the rise of the web, we saw the ability of scripting languages and other things to kind of rise. And so nowadays, actually, there are a whole lot of programs that you might have written in C++, but you would now write in another language. So I also don't want to dismiss those kinds of things as well. But Rust is appealing to this particular crew of people because it is truly low level and can actually do all of the things that C and C++ can do, which is something that is not necessarily true of other languages, or maybe they can, but it comes with a semi-significant drawback. The function. Well, did you want to get into that before we move on?
No, continue.
Okay. So the functional crowd, sort of what they bring to Rust is this. I already sort of mentioned this idea of type systems. So a lot of programming languages that have been popular in the last, let's say, decade have been dynamically typed. Maybe I'm projecting my own career on here a little too much, but I used statically typed languages first and then eventually moved into dynamically typed languages because the static type systems of the late 90s and early 2000s were not particularly expressive, and they often felt like they were getting in my way rather than helping me.
They can be stifling.
Yeah, exactly. Like I never really felt like I was getting all that much from it, and so when I moved to dynamic languages, I felt, wow, the language is actually getting out of my way and letting me do the actual work that I need to do. But as it turns out, the static type systems of those languages are not actually particularly representative of static typing in general. They're sort of representative of the particular languages that happen to become popular for various reasons. And so we've sort of seen a resurgence, especially in the last couple of years, of new languages that are statically typed that don't have those same kind of drawbacks. They sort of feel like they're almost in a totally separate category from the late 90s, early 2000s statically typed stuff. And so, as I mentioned earlier, the nice thing about static typing is that you're able to check all sorts of invariants at compile time instead of runtime. And so what the functional programmers bring to the table is one of the primary mechanisms by which we ensure Rust's core competency, which is pretty important. But what they get out of Rust is C-like performance instead of functional language performance, which functional languages can absolutely be performant, but they rarely are usually on the level of C. Like you can write Haskell that's as fast as C, but you're writing C in Haskell at that point. You're not writing like idiomatic Haskell code.
Okay, and now that we're getting into the features of the Rust language, there are the mutability discussion of variables in Rust is interesting. So variables in Rust are immutable by default. Explain why that is. Why is the default immutability useful?
So that is an excellent question, but I don't want to forget about the scripting crowd, the third constituency, before we super get into that, if that's okay.
Oh, of course. Yeah.
I have a Ruby tattooed on my body. I actually professionally am most known for working in Ruby before Rust stuff, so these are kind of like my people, this to some degree. So the dynamically typing crowd and I sort of say Ruby, Python, JavaScript, but it's sort of anything that fits in that niche. Perl,
the web app crowd.
Yeah, web app stuff or like any sort of dynamic typing thing. What they see in Rust is the first language in which a lot of those people can move to a lower level of the stack. And so what I mean is so I'll use Ruby because it's the community I'm most familiar with. So in Ruby, we've always said Ruby is slow, but you can make C extensions. And so if your app is too slow, just rewrite that part in C and then you're fine. And that's true, but C is so fiddly and difficult and sort of so different than Ruby that not very many people actually do that. And so a lot of people in the Ruby world know that they can drop down into C, but various things sort of prevent them from doing that in a practical sense. And so with Rust, they see a language that is much more similar to the languages that they work with. It still gives them that ability to go down the stack. And also, another thing is that Rust has specifically positioned itself as a language that's a good and welcoming place for people that are not traditionally systems programmers to learn systems programming. And so that is also appealing when they're told, don't worry about asking questions that might be quote unquote basic, we'll explain them to you rather than telling you to go read a book or level up noob or like all these other kinds of things that can be a problem. And so that's kind of what they get out of Rust. What they bring to Rust is an appreciation for developer experience. So a lot of people also associate programming in systems languages with like writing make files and dealing with linkers and all this kind of low level stuff. Whereas we focused really early on having Cargo, our package manager, which is much more similar to things that you see in the scripting world, like NPM or Bundler or Ruby Gems, all those kinds of tools. And so that is sort of like a quality of life improvement that the people from dynamic languages really demand out of their tooling. So I mentioned earlier that I moved to Ruby partially because I was frustrated with the developer experience not being that great of other tools. And so they're kind of always the perspective of how do we make this ergonomic? How do we make this approachable? And all that kind of stuff is kind of what they bring. The mutability thing. So this is also very interesting because in the history of Rust, it was something that was actually I don't want to say controversial, but the way that we talked about it has sort of shifted in different ways. So everything is immutable by default in Rust, it's true. And you have to explicitly opt into mutability. We've generally found that this is a good default simply because the vast majority of things don't actually need to be mutable. If you look through the source code of larger Rust projects, you'll find that somewhere around the area of 5 to 10% of variables end up actually being mutable, and a lot of other stuff ends up being immutable. But there's another aspect to the story that is a little more in depth, and that is the area around mutable pointers and concurrency stuff. So we know that one of the reasons why people seek out mutability is to help them with concurrency problems. And I'd mentioned that concurrency was sort of one of the three pillars of Rust that we really try to, the language tries to tackle head on. And so part of this is that we know that shared mutable state is the root of all evil, right? Like this is the mantra of the parallel or concurrent programmer. It's like we cannot have shared immutable state. But the key insight here is that you need both parts. You need the shared part and the mutable part for there to be the problem. If you have something that's mutable, but no other threads can talk to it, then that's totally fine. You're not going to have these kind of weird bugs. If you have something that's immutable, then you can share it totally fine. And there's not any problems because it's not going to change from out from under you. And so it's interesting because in Rust, sort of mutability and concurrency are kind of two ways of looking at the same problem. So we have this sort of approach where we actually don't do while we do this some degree of this mutability immutability tracking. It's also really about concurrency and how many things have access to the thing at the same time. So for example, you cannot have, even if you declare a variable mutable, you cannot declare a pointer to that mutable variable and have two of them from two different threads by default. That just does not actually work. And the compiler will at compile time tell you, hey, this is not actually doable. So it's actually even more subtle than just mutable immutable, which is also I can and have given entire hour-long things just about this one part. It's actually very interesting.
So you're saying that the mutability being tied into how we type the variables, that allows for compile time checking of potential thread safety issues.
Yes. And so sort of the way that you can think about it is a type like a mutex, for example, presents itself in the type as being immutable. But you can say mutex.lock and get a mutable reference out of the mutex, but it won't hand that mutable reference back if anyone else is currently mutably looking at the mutex. So from the type system's perspective, it is immutable because it is safe to share, but you can technically sneak mutable stuff out of it because it ensures this sort of contract of only one thing being mutably accessible at one given time. And so this is a complicated and thorough topic. There's all sorts of details here, but I guess that's just what I mean is it's more subtle than just, oh, this is mutable or, oh, this is immutable. There's a lot of different stuff that helps. And the compile time checking of these errors is also super paramount as well. So one of the really nice things about all this is it's checked at compile time. So I know, oh, I have a concurrency error in my code when I'm trying to compile it, instead of, I got a bug report that there was a crash. Let me see if I can figure out exactly what sequence of threads made this particular error happen. You know what I mean? That gets really complicated.
So we are in a world of increasing concurrent programming. So we should dive into some more of those details of the Rust concurrency. Computers are being built with more and more cores, but many programmers are not exactly prepared to utilize those cores, or they don't know how to utilize those cores. Rust is built to be highly concurrent and very safe, as you are explaining in terms of at least the mutability story. What are some of the other concurrency features of Rust?
So one of my favorites, actually, is that technically Rust does not know anything about threads at all at the language level. And what this means, so when you're in a systems language or a truly low-level language, things look a little different than when you're a higher level one. So when you're in a higher level language, you look to your language to provide you with certain capabilities, and if the language doesn't provide them, you have no ability to implement them yourself. So in a low-level language, it's actually interesting because, strictly speaking, Rust, the language, does not know anything about threading whatsoever. However, the standard library gives you access to these certain thread primitives and use the type system to talk about them. So it's nothing that is actually special cased in Rust, with one teeny tiny minor sort of exception that I only mentioned but to be 100% accurate, not because I really want to get into that particular thing at the moment. But I guess there's these two things called traits. So Rust has this trait system that are kind of like interfaces. You can say this type implements this trait, and then you can say this function only takes something that accepts this trait. And so there are two traits that are provided by the standard library to talk about concurrency. The first one is called send, And that is this able to be passed from one thread to another thread? And the second one is sync, which is this allowed to be accessed from multiple threads at one given time? And so it's not so much that the language understands threading deeply, it's that the interface provided uses these types effectively to manage the guarantees around concurrency. So why this is important is one example, Rust only provides operating system threads. We don't have green threads in the language or the runtime itself. However, because we have this low-level sort of access, alternate libraries have popped up that provide different concurrency and sort of threading models. So one of my favorite examples about this is this library called Rayon. And what it does is it basically gives you the ability to do parallel iteration. So say I have a problem that I have an iterator where I'm iterating over some kind of collection, and I want to modify each element of the collection as I'm iterating over it. If I wanted to turn that now into, okay, let's spin up 8 threads and process 8 elements of this collection in parallel, all I need to do is include the Rayon library and change the initial iterate call to a parallel iterate call. And it's able to safely, with all the same compile time guarantees of what the standard library gives you, do this kind of, now you're implementing this thing in parallel instead. And that's specifically because the language is very extendable by third-party things. And so part of this sort of ergonomics or taking advantage of these new cores is that we're able to have libraries that sort of give you higher level things on top of just basic threading and parallelism. So the standard library tends to provide primitives, and then people have built sort of richer things on top of that. And so there's all kinds of different things for all kinds of different use cases. So like, do you want a thread pool, that gives you n threads and just tell it to execute jobs? There's a library for that. Do you have a sort of specialized scenario around concurrency where you're providing a data structure that maybe, has particular properties? That's a thing that you can totally do. And so that's one thing that's really interesting in terms of actually taking advantage of the concurrency that our hardware is offering us now.
So now that we're talking about these different concurrency primitives, and you touched on send and sync, and I think these interfaces are traits. I guess they're called traits. I think these are pretty important to the conversation. Could you give another example, maybe of send and sync, and how the mechanics of send and sync, how you use these traits in practice?
So the function that spins up a thread in Rust is called spawn. It's in the thread package. So you say like thread : spawn, and you pass it a closure, and that closure executes in the new thread. So the way that the safety guarantee is provided is that the definition of spawn says in it, you're only allowed to access variables that are tagged with this particular interface. So, and the particular interface in this case being send. So like you're allowed to send this to the new thread. And so that's kind of how it provides the compile time guarantees about whether or not you're sharing things across or not. Because if you're trying to use a type in the closure that does not implement that type, you basically have violated the type signature of the function. And so it's just like any other function call where you're passing it the wrong type. So that's kind of like in practice how these things are used. It's like the interface uses them to properly define, okay, I can only take these things with certain kinds of guarantees. And then it just becomes a type error to call things that don't have the right guarantee, if that makes sense.
Yes, it does definitely make sense. Let's talk more about memory management, like some of the different memory management principles. So let's say I'm writing C code. If I'm writing C code, if I wanted to define a variable, I would need to call malloc to get space for that variable, and then later on I would need to free it.
Right, if you wanted to be on the heap.
Yes, if you want to be on the heap. In contrast, Rust has a language feature called boxing. Explain what it means to box a variable in Rust, and maybe you could contrast it with how Java does boxing.
Sure. So one kind of interesting thing about box specifically is that, again, it sort of repeats this theme of a low-level primitive that then you end up not actually using that much in practice. So we'll get into that, and then I'll talk sort of how it gets used and doesn't get used. So box works via a very similar mechanism to what's called RAII in C++ world, but the acronym is terrible and confusing, and so we try not to really use it. We say something more like it's called ownership, basically, and it's sort of a more holistic concept than this. But the basic idea is that you can have constructors and destructors, and when you instantiate a type, you call this constructor, and then it will do whatever happens in that constructor. And then whenever the type goes out of scope, we automatically run the destructor when something falls out of scope. So in the case specifically of box, basically the way that it works is, instead of you needing to say, call malloc, get this memory back, assign something to this memory, and then later I need to manually remember to free it, the free basically goes in the destructor, and so you automatically know that it gets cleaned up whenever it goes out of scope. So this is something that is like a significant ergonomic improvement, and also helps correctness, because you can guarantee that you match exactly one free with one allocate. C++ has a very similar feature called unique pointer, but it is not the same because it does not have the same level of guarantees about its correct usage. It still requires that you use it in the proper way, and if you use it improperly, you will still have bad things happen, whereas Rust does not actually make that. That's not a problem.
You mentioned this concept of ownership and lending. Could you talk about these in more detail? Explain how ownership works and what it means to borrow in Rust.
Yeah, this is kind of the core of Rust's new innovative feature. And so it's interesting because from a programming language theory perspective, it's possibly the most interesting thing about Rust. But it's also, like, when we talk about it too much, it used to be the thing I would say, like, you want to use Rust because of this feature. But it turns out that, like, most people are not programming language enthusiasts, and so they care more about the high-level stuff than, like, the specific details. Basically, the way that it works is this. Every single value in Rust has some sort of variable binding. Other languages call them variables. We call them variable bindings for some reasons. But basically what happens is your particular variable is responsible for deallocating that particular value that it holds a reference to. So if I say let x equals box 5, that will put a 5 on the heap. And now x is called the owning binding. So specifically, ownership is about who is responsible for destroying something. So if I would pass x to another function, instead of it being the original scope where x was defined, instead it would be destroyed whenever that function I'm passing x to goes out of scope. And that's when the variable would get destroyed. But if you have just this one feature, like this solves the I need a single free for every single allocate call problem, but it ends up being incredibly unergonomic, because you have to, if you pass a variable into a function and you still want to use it outside the function, this means that now the function has to pass the variable back to you, right? Because like we have to pass this single sort of thing around. And so this gets, on its own, this is incredibly unergonomic. And so we introduced this concept called borrowing, which basically promotes the idea of, hey, I'm going to use this variable of yours, but I'm only going to use it temporarily, so it shouldn't be destroyed when I'm done using it. And so this is very similar to references or pointers in C, but the idea is that you know which ones you do want to destroy the variable and which ones you don't want to destroy the variable. And so most functions actually take their arguments by borrowing rather than by ownership. So they're only temporarily using the thing. And this makes it significantly easier for people actually using the programming language. You don't have to repass back every function, every argument that you passed into the function. But this introduces another problem, and this is sort of the problem with pointers. And that is, once you start having two pointers to the same location in memory, you need to make sure that the underlying data does not get deallocated while any of those pointers are active. And so Rust has this concept of lifetimes, which basically allows us to talk about the scope that a reference is active. And so to know, okay, this memory cannot be deallocated while there's still an outstanding reference referring to that particular bit of memory. And so this is kind of how we provide the safety aspect of this feature. So we can guarantee you that if you have a reference to something, that it will be valid 100% of the time and not have its underlying thing freed out from underneath it. And so these kinds of things, ownership, borrowing, and lifetimes, all sort of tie together into this package that makes up Rust's memory management situation. And I also want to emphasize briefly that this all happens at compile time. So there is absolutely no runtime overhead. So it compiles the exact same code as if you used a C pointer. It's just got this compile time checking along with it.
Right. And so to be clear, Rust does not use a garbage collector. For anyone who wasn't completely following the conversation.
Yeah.
And this is, one of the big draws of Rust. So Could you talk more about the holistic picture of the memory management techniques that Rust uses in contrast to how things would work in a garbage collected language?
Yeah. So basically, the fundamental sort of, there's two kind of reasons in which a GC is inappropriate for a lot of Rust use cases. The first one is that a garbage collector is not necessarily deterministic. So basically, you're using a value. So let's say I'm using Ruby. I say x equals 5. Now I have a integer value, and of course this is all implementation dependent because like JRuby will do shenanigans and whatever. But like at a basic level, whenever you declare some sort of variable in a language that uses GC by default, it gets put on the heap, and then the GC knows, okay, I've allocated this one thing on the heap. Now our function ends, and x is no longer in scope. Some time passes, and then at some point when the garbage collector runs, it looks and says, oh, x is no longer in scope. This now needs to be freed. But there's no sort of, you can't make any guarantees about how long it's going to take after the function ends before the GC will free the memory. And so this is a significant problem in a number of different problem domains. But it's just a general, like, the more non-determinism you have, the harder it is to know exactly what the properties of your system are, and sometimes the details of those properties are incredibly important. The sort of second reason that a GC is not appropriate for something like Rust is that a garbage collector then means that you have this code running in the background of your process all the time, the garbage collector, and that means that you need to then port this code to every platform that you need things on. You need to make sure that your program contains this runtime or has access to this runtime in some fashion. And so it introduces a relatively heavy dependency on the actual code and language itself, which is not appropriate for all domains. If you're working on a microcontroller, for example, you don't want a GC taking up your very, very limited resources. And so it's kind of these two things, the non-determinism and the heavier resource usage that sort of make a GC not really appropriate. The final thing that's important about this is that people often forget that a garbage collector is only good for managing memory itself. There are all kinds of other resources that your program needs access to other than memory. So maybe you open a file, maybe you make a network connection, maybe you have some sort of other resource you need to manage. And so a GC cannot really help you make sure that your file gets closed whenever you're not using your file anymore. And so that's also a big part of it. Is garbage collectors are incredibly useful tools, and I don't want to say that they're worthless because they're definitely not. I mean, I love garbage collected languages just as much as a lot of other people do, but it's a matter of trade-offs like everything else in engineering. And so sometimes they're very useful, but other times their drawbacks outweigh the benefits.
The nature of money is changing, and software engineers are the creators of that change. On Software Engineering Daily, we've done shows about Bitcoin, automated trading, Ripple, and other financial technologies. One thing is clear: there has never been a more innovative time in financial technology. Untapt has jobs at the world's leading FinTech companies. Untapt is a platform for matching software engineers with jobs at FinTech companies. Sign up at untapt.com/sedaily and find a job in FinTech. If you're invited to interview, Untapt will send you a collection of 5 books relevant to both your interview and this week's episodes on Software Engineering Daily. These are books like Cracking the Coding Interview, or Manning books, or O'Reilly books, and they're really going to help you get the knowledge that you need to get the job that you want or create the piece of technology that you want to see brought into the world. There's more at untapt.com/sedaily. That's untapt.com/sedaily. Untap your talent today at untapt.com/sedaily. Now let's get back to this episode of Software Engineering Daily. Rust runs on the LLVM, which stands for Low-Level Virtual Machine. Explain what the LLVM is.
So LLVM is really unfortunately named because it is not actually a virtual machine. or rather, it's a virtual machine for a certain definition of virtual machine. So one way that you can kind of think about LLVM is that normally a compiler would, so like say, let's take a C compiler, for example. A traditional C compiler would take the C source code, it would parse it into an AST, it would do some kind of optimizations and whatever other shenanigans that it wants to do on that data structure, and then it takes that data structure and translates it into machine code. So that basic process is very useful and reliable, but there has been some things that have happened that have made this, let's say, a little too simple. So one example is, if I now want to write a compiler in a different language, I have to re-implement all of that aspect of translating this, translating my AST into assembly code. And I don't necessarily I have to rebuild things like optimization passes or safety checks or any of the kind of transformations that I want to do. I have to re-implement them for every single language. And so LLVM is kind of like a platform for building compilers. So the idea is that instead of your compiler emitting assembly language directly, it emits this thing called LLVM IR, which is kind of like an assembly language, but not quite as low level as one. It's like a little bit higher level. It has some type information and some other things. And then, so what happens, so we'll take Clang, because I was using a C compiler earlier. So normal C compiler, parse, AST, do transformations, spit out to binary. So the way that Clang works is it does the parsing, it gets an AST, but then Clang takes that AST and it produces LLVM IR, and then LLVM handles doing all the optimization passes and all that other stuff on the LLVM IR, and then it does the actual generation to the final binary. And what this means is we now have, excuse me, we now have this kind of platform where we can write optimization passes, safety checks, all kinds of these other things, and have them be used across any language that oh man, I just coughed now all of a sudden. Sorry about this. We have this platform by which I can write a compiler today, and instead of me having to re-implement all that stuff, I just produce LLVM IR, and I get all of that manpower that Apple has put into and others have put into LLVM IR for free. And so this is really, really powerful because it deduplicates the work of improving the performance. But yeah, so it's not really a VM in the sense that LLVM does not give you a virtual machine that your code then is interpreted or executed in. It's more like a compiler toolkit for building compilers. And one reason this has been so advantageous, if I don't need to do all that work, I can write a brand new language and take advantage of all of that other work that's been put in. So it's very easy. It's significantly easier to bootstrap a brand new language on the LLVM platform and have significant amounts of performance and like other things kind of related to that. So the compile to LLVM is like a very popular strategy for a lot of new languages because they don't want to have to do all that work themselves, basically.
Languages such as Swift, right?
Yeah, absolutely. Swift is another great candidate. So, and the other nice thing about this is too, when we improve LLVM in some way, it helps everyone that uses LLVM. So like the Rust team has contributed some patches to LLVM for various things that we found or wanted. And then the Swift team is able to just instantly take advantage of those benefits that we, this is like the open source dream, right? And vice versa, when Swift or the Clang people or whoever else improve LLVM, it improves it for all of us. So I think this is a really, really positive thing just overall, for sure.
We saw with the JVM that, if you build this virtual machine that is really powerful and has a lot of work put into it, people will build other languages on top of it, like Clojure or Scala. But so is LLVM analogous to the JVM, or what is the relationship there?
It is only in that abstract sense of it's providing a platform for other things to build on top of. The significant difference is the JVM is like an actual virtual machine that's running. It's like if I want to use Scala, I install the Java virtual machine, and then I use Scala C to produce class files that end up running on that virtual machine, right? So it's sort of like a runtime virtual machine. Right, like a big feature of the JVM is that it has a just-in-time compiler and it uses the runtime information to produce, better results. LLVM is a virtual machine only in the sense that it provides this ability for other people to write code that then runs on it, But the difference is that you don't have LLVM running on your computer. Like, to use Rust, you don't install LLVM. LLVM is more like a library that the Rust compiler uses inside of itself. And so the final output of a Scala program is class files that run on the JVM. The final output of an LLVM using compiler is binary code that runs on the machine and has no connection to LLVM at all.
Okay, I get it. So when it refers to low-level virtual machine, it's referring to the level at which the final version of the code runs on, which is as low as it gets, binary. Whereas with the JVM, the output of your program is like bytecode instructions that run on the JVM, which then get turned into lower level commands.
Right. One way to think about this is like platform support. So let's say I have my C compiler and I'm trying to target x86. So when I write that output to binary, I need to deal with the machine that the x86 specification gives me, right? Like, I need to output x86 assembly code, I need to follow its rules and do all that stuff. If I then want my C compiler to spit out code that works on ARM, I then need to target the ARM machine and have it spit out the appropriate assembly instructions and do all the right things that ARM needs me to do. So the way in which LLVM, the name, refers to the fact that LLVM says, instead of these individual platforms, we're going to provide a sort of our own machine that you're targeting, and then we know how to compile from that to each of these other platforms. So it's kind of more like that. Like, that's where the name originally comes from. And this LLVM is very old, so it was named during a time whenever the virtual machine like terminology was not necessarily as like widely known amongst regular old programmers. And so it's more of like the compiler sense of machine than it is like an interpreter VM kind of virtual machine.
So we don't need to talk about too much of the LLVM beyond what we've already discussed, but I've done 0 shows on it, and I get the sense that it is this super important development, and it's going to shape the direction of programming and programming languages into the future. Can you give me a sense of the implications of the LLVM and what is in the future for the project?
So one of the big things that, any project that's used by a lot of people always has drawbacks, right? Like, you can't, a lot of people say you can't say that you truly love something until you can describe why you hate it, right? So one of the significant flaws of LLVM is that it actually is sort of designed for originally C and C++ code. So it's actually not very good for garbage collected languages. And so a significant area of improvement in LLVM in the future is the way to, like, how does LLVM properly support languages that need to be sort of garbage collected? Like, if you make this analogy that like LLVM is a library, so you don't have to think too much about the low-level machine stuff, like if I'm making a language of the GC, I still have to write and implement the GC myself, and somebody else's GC language, they have to implement and write all the GC stuff theirself, and so there's sort of no abstraction for helping with garbage collected languages. And so I'm not sure where it is on their priority list because I don't follow the LLVM project's development that closely, but I do know that it's sort of an area in which it is sort of weak right now and could definitely use improvement and will help in the future, and there are people that care about this topic. So that's one area in terms of where LLVM goes into the future. I think that the significance of it is the decreasing the amount of time it takes to bootstrap a new language into the world. So, for example, when building Rust, like it took us 6-ish years to get to 1.0, and that's with LLVM's help. If we had to implement all of the optimizing stuff that LLVM gives us for free, it would have taken another, couple of years to make Rust actually ready. And we're Mozilla, like we have resources, and like we have people who are able to do these kinds of things. But if you're like a hobbyist and you want to make a new programming language and you want it to not be completely and utterly slow, LLVM gives you a really great option to take advantage of other people's work, so that you can focus on building your language instead of focusing on obscure optimization shenanigans, basically.
So let's get back to talking about Rust in a broader sense. What about the build system for Rust? Tell me about the build system. What is unique about it?
So fundamentally, Rust has sort of two things that are used to build Rust code. The first one is Rust C, the regular old Rust compiler. And it sort of knows how to compile a Rust program, on its own. It's just like any other compiler. It's very similar to GCC or Clang or anything else. But then we have this build tool on top of it called Cargo. And what's interesting about Cargo is a couple different things. The first one is that I think that Cargo is one of the few times that a language has sort of shipped one of these tools with the language itself. So, I come from Ruby world. Ruby Gems is included in Ruby, but Bundler is not, for example. Python does not have a standard package management solution shipped with it. C and C++ don't barely even have the notion of packages, let alone a package manager. Notably, Node includes NPM along with Node, but NPM is actually a totally separate entity, in and of itself, and they're doing development totally divorced from, Node on its own. I shouldn't say totally divorced because they all know each other, obviously, but I mean, it's not like one overarching organization is developing all this stuff in tandem. Whereas we thought that it was extremely important. So some of the reason this happens is because those tools were developed after the fact. So Ruby was released in 1995. Bundler was released somewhere around 2009. So obviously it's not being shipped with Ruby by default because it didn't even exist when Ruby was shipped. So when you're making a new language, you often have the ability to learn from the hindsight of other languages. And so specifically with Rust, we saw that these kinds of tools for managing your project at a higher level are incredibly important for developer productivity and ergonomics, and also setting up a good open source ecosystem and all this other kind of stuff. So we made an investment early on to build this tool on top of the Rust compiler called Cargo. And Cargo is sort of a more high-level build tool where you can say, here is my source code. Also, I depend on these 5 projects. Just please build my project and include those dependencies and just deal with it. And so Cargo automatically knows how to fetch open source packages from a package manager. It knows how to fetch all of the dependencies of those dependencies. It knows how to make sure that all of that stuff is coherent. In a sense of, this depends on this version, that depends on that version. Is there going to be a problem, or does this work or not? And then it knows how to compile all that stuff and link it into your code, so you don't have to worry about setting linker flags or dealing with all that kind of sort of low-level options about things, and then merge that with your code and produce kind of the final output binary.
Would Cargo make a call to another build or installation tool like apt?
So strictly speaking, no. However, practically speaking, we, as a pre-processing step for building a package, we allow you to execute an arbitrary Rust program. And so those kinds of, those arbitrary Rust programs can call out to whatever other build tool that you want. So for example, say that you're writing a library that is built on top of Lua. You have Lua bindings to Rust. There's 5 of these already. So it's a very realistic example. If you don't have Lua installed in your system, the build script says, oh, you're about to build this project. We need the Lua dependency. Maybe I want to try installing that through your system's package manager first. Maybe I want to compile, because Lua is a particularly lightweight thing. Maybe I want to compile the source of Lua and just build it specifically for this project. Maybe I want to query the operating system to see, maybe it's in a non-standard location or something. But that's all part of this extensibility system. It's not really part of Cargo inherently, other than we let in this release valve so that we can play nice with other, parts of the software ecosystem.
Let's zoom out even further. What are the applications that people are building with Rust? What kinds of things are you seeing?
So, what people are building with Rust? A couple weeks ago, we started this page specifically that we like to call Friends of Rust. And it's basically organizations that are using Rust in production. And so there currently are somewhere in the area of 20-ish companies that are using Rust in production on there. I haven't counted in the last couple of days. But they're used for a wide variety of different things. So, for example, the oldest sort of production user of Rust, or the oldest major one that's still going on today, is this company called Tilde. And they are known in the JavaScript world, specifically Tilde founder Yehuda Katz built Ember.js, was heavily involved in Ruby on Rails before that. And their usage of Rust actually led Yehuda to now be on the Rust core team as well, because of his sort of investments in the Rust ecosystem and all that kind of stuff. But what Tilde does is they sell this product called Skylight. And Skylight is a performance monitoring solution for Rails apps. So what happens is you install the Skylight gem into your Rails application, and it sends metrics back to their servers that you can then get reports on. That Ruby gem is actually implemented in Rust. So when you install their monitoring system, you have Rust code running on your computer now. And so they've been shipping Rust code to thousands of users for the last couple of years. And this is an area, again, where the low-levelness of Rust really shines. You can embed Rust in other languages really, really easily because it doesn't have a garbage collector, because it does not have a complicated runtime. That's a very reasonable path to sort of take. So that's one thing. Another company that recently has announced Rust stuff that I'm really excited about is Dropbox. So Dropbox recently re-implemented the way that they store all the files and bytes on all the hard drives. They're originally on AWS, and they sort of moved to their own data center. And as part of that, they basically wrote a custom file system in Rust. And so now kind of the core of Dropbox is actually running on Rust code.
Yeah, we did a whole show about that. We actually didn't go into the language decision in detail. From your point of view, why did Dropbox choose Rust to build the language or to build the file system?
So they've spoken about this a little bit, and so hopefully I remember the details correctly and I don't misrepresent them on this. But basically what it boils down to is when you're doing this kind of low-level work, you need precision, but when you're working at Dropbox's scale, you also need accuracy. And so like a language that is both low-level and safe has significant advantages over, other languages that may be safe but a little slower, or, just as fast but dangerous. So I know that they evaluated like C, C++, and I believe they usually use Go. So I think that they looked at Go briefly for this, but I can't remember if they did or not. But they ended up choosing Rust, and from everything that I have heard, they have been very, very happy with that decision, and are sort of looking to eventually do some more Rust in the future. Another area that we just recently announced a statistic I'm really psyched about is, of course, Mozilla and Firefox. So we're putting Rust code in Firefox. If you download Firefox on OS 10 or Linux today, there is Rust code in there. And in 2 releases, it will be on Windows. So 12 weeks-ish, which maybe 6 weeks by now, actually, come to think of it. Sometime in the near future, there will be Rust code in Firefox. And one of the cool things about that is it's a very small edge case, so it's an MP4 parser. If you load certain MP4 files, the headers and stuff will be parsed in Rust. But we have metrics on this, and the Rust code in Firefox is executed over 1 billion times and has had 100% success. There's never been a crash or an error or a problem related to the Rust code in Firefox so far. So holding my fingers to keep out that perfect streak, as long as possible. But so far so good. We've seen extreme levels of reliability. Obviously, Firefox is used by hundreds of millions of people around the world. You all know about Firefox. I don't need to tell you more about that. But it's starting to use Rust as well, and that's been a really big, kind of example. There's all sorts of other companies using like various cloud things, either servers or there's a company that just recently announced Rust support called Algorithmia, which is a marketplace for algorithms. So you can like write a program and then host it in their cloud and then pay people to, use your program kind of thing. And so they recently announced support for like having Rust in those containers, and they're using some Rust stuff around that. So there's just all kinds of stuff sort of all over the place. There are 2 different cryptocurrencies using Rust now, which is kind of, interesting. I personally am a little skeptical on the idea of cryptocurrency, but it's cool to see people doing neat stuff, that involves a lot of network stuff and cryptography and all those other things. But yeah.
So you have touched on this a little bit in this conversation, but how does Rust compare to Go? I mean, some people say that Rust is a competitor to Go, but other people say they are totally orthogonal concerns that happen to look somewhat similar. But what are the applications where Go is a good fit, and what are the applications where Rust is a good fit? Are they overlapping? Give some more color on that.
So the way that I like to look at this problem is twofold. First of all, a lot of people see them as similar because of an accident of history. And secondly, the languages are very different, but that doesn't necessarily mean there's no overlap. So let me get into this accident of history first. So Go and Rust both became known to the world at roughly the same time period, like within a year of each other. And Google originally described Go as a systems programming language. And Rust is also described as a systems programming language. So a lot of people went, oh, Mozilla's making Rust, Google's making Go, like whatever. They're basically the same thing, just from these different organizations, which is a totally reasonable distinction to make. The tricky part is that what Google meant by systems was different than what Mozilla meant by systems. So Google meant systems as in like cloud servers, like I'm running application layer like stuff to deal with the network and all these kind of servery stuff that Google really cares about. Whereas with Rust, we meant like low-level programming, no GC, all that kind of stuff. And so what this means, though, is that there was originally like a lot of confusion about this, and a lot of people thought they were a lot more similar. Another problem with this, historically speaking, is that early Rust actually looked very similar to Go today. Like at one point in Rust's ancient history, it actually did have a garbage collector. Those times are sort of long gone, and this is not really about the history of Rust exactly, but that also contributed to this kind of people thinking that they're sort of for the same thing. Now, in terms of the way that I see these languages together, the way that I like to think about it is Rust is a low-level programming language that's looking up the stack, and Go is a high-level programming language that's looking down the stack. So you can kind of think of Go as being like a lower level Ruby or Python, and Rust as being a slightly higher level C or C++. And what this means is they're kind of looking at each other, right? Like Go is looking down, Rust is looking up. But there is a gap in the middle there, I think. However, programming is all about trade-offs. Like you can write your blog in C if you want to. That doesn't necessarily mean that it will be a particularly ergonomic or like joyful experience, but like, at the end of the day, Turing completeness means that all programming languages can be used for the same, all the same things if you really, really wanted them to. But it's a matter of sort of like trade-offs and characteristics. So Go has kind of found a specific niche in which it is like extremely useful, and a lot of people really love it. But Rust is a bit more broad and a bit more low-level focused. So if you need to do something that's truly low-level, like write a file system, then Rust is a better question, is a better answer to questions asked. If you're doing something a little more high-level, things can start to be a little bit blurry because I've heard some people say that like they're not writing new stuff in Python anymore because Rust feels just barely lower level to them, yet is significantly faster. But I think that those people are generally in the minority. But if you're writing like a networked service, Rust will make you deal with a lot more fiddly bits, and it will, there's a lot more complexity involved because we care so much about things like correctness and performance. Whereas Go will kind of let you get up and going, no pun intended, significantly faster and possibly, a little more ergonomically. I will also say that just generally speaking, like we on the Rust team, and it seems to be the Go team as well, like don't really see any bad blood, or like we don't want a like, yeah, Go versus Rust, Rust is awesome, Go sucks. Like that's like, we are really not looking to have that kind of relationship with the language or its programmers. I think that's also part of it too. Like sometimes people on the internet like to try to start fights, and so they'll say like, Go Rust, fight. But we're kind of like, why are we fighting? There's no reason for this. So our perspective is much more one of like, Go is doing really great things. They made significantly different choices than we've made, but that's because the problems they're trying to tackle are significantly different than the problems we're trying to tackle. So seems like everybody's doing good work.
It's like when people compared Python and Ruby and were like, these are the same language.
Yeah.
And they kind of weren't. And they have vastly different applications, and nobody really thinks of Python and Ruby. Neither one of those languages won, right? Like they weren't having some fight. So it seems like that to me. Okay, well, we're beginning to draw to a conclusion of this conversation. Rust was voted the most beloved language of 2016 on Stack Overflow. So I guess I'll close off by asking you why that is. Why is Rust so beloved, and where are we going with Rust? Why should people invest their development careers in learning Rust?
Yeah, so I mean, I am obviously a little biased since I've been pouring the last couple of years of my life into Rust, but I was incredibly happy to see that statistic because it's kind of validating all the work we've been doing over the last couple of years. I would say that my speculation as to why people voted that way is a couple-fold. First of all, it's sort of breathing a bit of fresh air into this space that has not seen a lot of new improvements lately. Secondly, I think that one of the advantages of Rust is its openness. So because of Mozilla's sort of open source nature, everything has been open source for an extremely long time. And in fact, Rust is not even really like controlled by Mozilla. If you look at the people who are actually like have commit and are on the various teams and are involved, it's like 50% Mozilla people and 50% other. So in a plurality sense, like we're the largest single organization of people contributing to Rust, but it's not even really like, we like to think of ourselves as being separate from Mozilla itself. In many ways, but part of that open source ethos that was instilled by Mozilla means that we spend a lot of time talking to people online. So I have people that join our IRC room and they ask a question and I answer them and they say, wow, I've never had the people who are making my programming language answer my help questions before. And on top of that, you're really all friendly. So one of the things we strive really, really hard in the Rust world is to not be jerks and to, just generally speaking, like sort of like what I said about the response to the Go versus Rust thing. It's like, chill out. They're doing good work. Why do we need to fight each other? Like, let's all just be actually nice and enjoy programming instead of like being angry to each other all the time. And so we do a lot of work to sort of also bring people who have that same kind of perspective of like, oh, you're new to this? That's totally cool. I used to be new to this. Let's help you out. And so I think people sort of see that kind of outreach as being very positive, and they sort of, understand that we actually care. If you're a big Rails app running a Rails shop, you do not really necessarily get support from either the Rails team or the Ruby team. You kind of just do your thing. But like we, directly talk to people who are using Rust that want to talk to us to try to help them. Like, where are your pain points in language? Can we make this better? Like, we treat it more like a customer service thing than a lot of open source language projects do. And so I think that care and attention and wanting truly to make things better for our users is something that they seem to appreciate and care for us right back.
All right. Well, Steve, thanks for coming on the show. This has been a great conversation. I am a big fan of your work on, I guess your work spreading the word of Rust. I mean, I watched several of your YouTube videos and they were really entertaining. So cool. Well, thanks for coming on Software Engineering Daily and talking about Rust.
Yeah, thanks for having me.